All right, good afternoon, folks. Welcome to the Office of the Chief Scientist Science Seminar Series. My name's Andrew Paul, and I'm a Senior Science Advisor with the Office of the Chief Scientist and am your host for this year's fall seminars. So on behalf of our whole team, I welcome you to today's event, which, like many of our talks, is going to be another fascinating talk. In fact, today at lunch, I took a walk along the Bow River, and I couldn't think of really a better medium than water to acknowledge our relationship that we have with the land. As I was looking down at the Bow River and the water at my feet, I was just thinking that water is going to travel through the traditional territories of Nakota Sioux, Blackfoot, Métis, Iroquois, Cree, Saulteaux, and Dene nations, along with others. So I ask you today, in the spirit of reconciliation, that wherever you might be located, that to think about the water that gives us all life, and think about the journey that it's going to take through the traditional lands of First Nations and Inuit people, as well as the homelands of the Métis. And it's in this notion of sharing that we present these science seminars. It gives us an opportunity to exchange knowledge and interesting science that's happening across Alberta and Canada, and we want to do it in an open and learning environment. So today, if you have any questions or comments, please feel free to enter them into the chat window or chat box in Teams. And at the end of the presentation today, I'll work my way through those questions and comments in the order that they're received. Your audio and video will be turned off today, and that's just given the number of participants and to keep our call quality as good as possible. Those audio visual capabilities are turned off today. So use the chat window to enter those comments, and I will be following that throughout the presentation. So with that, I'd like to introduce our speaker today, and that's Dr. John Pomeroy, who will be presenting on global water future outcomes for Alberta. Dr. Pomeroy has conducted research on the hydrology of Western Canada for over 40 years and has particular expertise in snow and ice hydrology, agricultural, forest, and mountain hydrologic processes, instrumentation, and modeling. He leads the Global Water Futures Program, which is the largest university-led freshwater research program in the world, and he's the leader of the new Global Water Futures Observatories facility. It's with the University of Saskatchewan Cold Water Laboratory located in Camware, Alberta. Dr. Pomeroy is the Canada Research Chair in Water Resources and Climate Change, UNESCO Chair in Mountain Water Sustainability, and he co-chairs the UN Advisory Board on the International Year for Glaciers Preservation. So with that, Dr. Pomeroy, I'll turn it over to you to start your presentation.
Okay, great. Thank you so much, Andrew. And it's a great honor and pleasure to be speaking to this forum. I want to acknowledge the support from the Alberta government over the years of research in the mountains and prairies here, from what's now Alberta Environment Parks, or Alberta Irrigation and Agriculture, or Alberta Forestry and parks. These have all been instrumental in the research results that I'll be showing you. So I'll jump right into it with starting off with just a little bit of a background on what Global Water Futures is. It's a program funded out of the Canada Research Excellence Fund, led by 4 universities. U of S is the primary, but the others are big contributors. And then with a total of 18 universities with significant involvement through individual faculty, including University of Calgary and University of Alberta. And so it's become the largest freshwater research program in the world that's led by universities. And on our recent metrics, it's also the most published in the world. And in terms of citation, I think we're 4th. So it's a globally important research program, and I'm going to zoom in on some parts that are particularly relevant to Alberta and Alberta's future. The aims of Global Water Futures, the first was to place Canada as a global leader in water science for cold regions, and I think we've done that. The things that we propose internationally, like the Glacier Year and now a new decade of action for the cryospheric sciences, have been adopted by the United Nations. Things that we proposed in Canada, such as developing a Canada Water Agency federally so the federal government can better coordinate its roles, have been adopted. And so we're proud of that. But the also to address the strategic needs of the Canadian economy and how we adapt to changes and manage the risks of changing water and extreme events like the floods and droughts that have afflicted so much of Canada more intensely in recent years. And so this meant really making sure that this is a user question-led project, and we've done that. We started with a massive user engagement initiative in 2016 with hundreds of users to find out what were their key questions. So we designed the program around that, and then our call for proposals for projects within Global Water Futures, the 64 projects and core teams, were all designed to address those questions. So, improving disaster warning being a big one, and harnessing data to predict water futures with numerical models being another objective, or informing adaptation to change and risk management. And these all came from user questions and user demands. So that we did that first, and we started early with our Indigenous engagement. We had our first national science meeting on First Nations territory at Six Nations of the Grand Rivers in Ontario, and have kept that up with a number of Indigenous co-led projects as well. So we view ourselves as a science program in the broadest definition of science, that it includes knowledge as well as traditional Western sciences. The program as it stands recently, we're still updating this, but we've put funding out to 23 universities across Canada, over 200 professors at those universities, well over 500 partners. The publications have, I think, reached 2,600 refereed journal articles, and over 2,000 researchers hired under the program. So it truly became massive. And the original budget allocation of 77.8 million from CFREF, we're able to supplement that with university contributions and contributions from various users and partners across the country, including the Alberta government, and bring the budget up closer to getting close to $1/3 billion, which is remarkable. So a lot of that's in kind, of course, but it's a big budget. It was supposed to wrap up in 2023, but we had the pandemic, which slowed down a lot of things. So we have a no-cost extension to the end of August next year. And we're focusing right now, we're wrapping up the projects and core teams and writing a synthesis report of the science and outcomes across Canada. And so much of what I'm showing you is coming from the material being developed for that synthesis. So partway through GWF, we published a paper talking about the water futures in Western Canada. And this is a combination of modeling outcomes and scientific expectations from ecologists working in a multidisciplinary way to look at what the Saskatchewan and the Mackenzie River basins might look like by the end of this century. We anticipated new crops and northward expansion of agriculture, loss of mountain glaciers, loss of montane forests, and expansion of shrubs and grasslands, expansion of grasslands further north into the boreal forest, expansion of broadleaf deciduous forests further north, and loss of evergreens, and large increase in wildfires. So we wrote up a lot of this about 5 years ago, and even the last few years, so much of it has been occurring. But also then the hydrological changes associated with this, increasing risks of winter and spring rain on snow and rainfall-driven flooding, declining snow-covered periods, loss of low elevation snowpacks, and retreat of glaciers causing a greater risk for a hydrological drought in the summer. And we wrote that up before 2023 hit us. and it sure hit us. But overall, because of the long-term increase in rainfall that's predicted out of many models, an increase in the flows of the Mackenzie and Saskatchewan River with an increase in timing. And I'll dive into that in more detail shortly. But also the drying of the boreal forest in the summertime being a big concern for wildfire. And then the drier summers being something that would increase irrigation demand and probably improve the economic prospects of irrigation, requiring new reservoirs in many cases. And so Alberta's already on that. And then wetland drainage proceeding over mostly the eastern prairies, but some of Alberta in response to wet years, um, and changing crops, taking advantage of the longer frost-free periods. So let's zoom into that a bit. One thing we did at Global Water Futures was couple our water observations, data management, prediction, and knowledge mobilization strategy. We focused on 7 basins across the country, totaling about 5 million square kilometers. That's the size bigger than the European Union, so this is a large undertaking. And then we tried to pull this together in such a way that we could get the information out to users in some actionable format. And users have many, many different interests and demands and ways and capacities to take on information. So we learned a lot in how to do it effectively, at least we hope effectively, and everything from apps on phones to databases on supercomputers to papers describing it to simply sitting down with groups and explaining what the results are. And as the program started to wrap up, we said, well, we have this incredible network of observation sites across the country, and it would be a very positive thing to be able to keep them going. In fact, many had been kept going since the early 1960s, and we didn't want to shut them down, and we weren't sure how to sustain them economically. So we applied to the Canada Foundation for Innovation's Major Sciences Initiative for a project we call the Global Water Futures Observatories. And that was approved with a larger consortium of universities. We're the only ones in the West, but the others, there's a large focus on the Great Lakes region and Northern Canada. And this runs to 2029, and it's renewable. It's also expandable. So we're in discussions with the University of Calgary and University of Northern British Columbia to increase our network in the West. And the total program budget is just over $40 million a year. CFI covers 40% of those costs. We were able to get the universities and a few other funds, even NOAA from the US came in to help us get going for the first couple of years. And we're still working on finding the matching funds to keep it going. But it's an early warning system for freshwater. You can see the map of sites across Canada. Some of these are sophisticated hydrometeorological observation stations. Some are boats out on lakes collecting water quality samples, even underwater gliders that go under the Great Lakes. Some are research camps up in the north, instrumented glaciers I'll get into a bit. We have deployable systems like drones and very sophisticated chemical analysis labs across the country that do everything from microplastics to inorganic, organic chemistry, toxicology, and eDNA analyses. So that's I think these are really a gem of Canada. And some of these sites like Marmot Creek was started up in 1962 by Alberta and the federal government. We still have that going, and these things are gems of information that you just can't get any other way. And we have 50 staff employed with us across the country, data managers, technicians, and others to get the information out. As we zoom into the sites across the West, in the Saskatchewan Churchill Nelson Basin, we have a cluster in the Rockies, and that I'll get into in a bit. We call the Canadian Rockies Hydrological Observatory. We operate that out of Canmore, Alberta. That's where I'm coming to you right now from our cold water lab in Canmore. Then we have prairie sites in Saskatchewan, going from irrigation sites and water supply for Regina up into the boreal forest. We also have off the map here a site up in the Peace Athabasca Delta. It's more a water quality observation site. And zooming into the Canadian Rockies, we have a number of these instrumented basins, such as Fortress Mountain or Marmot Creek, as I mentioned. And I'll talk about Peyto Glacier. I was up on Athabasca Glacier yesterday. It's melted 7.6 meters downwards this year. So we come up with information pretty rapidly on that. A lot of studies of forest hydrology and soils associated with groundwater systems in the mountains. So it's not just the snow and ice, it's tying into that and into beaver controlled wetlands and other processes that control and generate stream flow. And we're very interested in land use change as well as climate variability impacts on stream flow generation. The glacier monitoring always gets people's interest. This is Peyto Glacier. It's the longest intensely monitored glacier in the world. And the records go back to 1897, but intensive science since 1965. So it's a glacier science gold mine in Banff National Park. So that's a drone. We fly over it with LiDAR to map its changing elevation and reflectance, and we have stations up on the ice and off the ice there as well. As you can see, it's starting to disintegrate and fall apart, and that's one thing I wanted to bring up today. So how much has it fallen apart? Well, a lot. It's retreated 443 meters, almost half a kilometer in 5 years. So its decline is accelerating. And on the left-hand side, there is a map of its extent from 2019 to what it is now in 2024. And you can see the individual images. And that heat dome in 2021 really knocked the stuffing out of Peyto Glacier. That's my technical description of it. It retreated almost 200 meters in that 1 year. As you can see, a lot of it started to break up, melting from underneath as it melted into the new proglacial lake there. That lake didn't exist until about 2011. I had an experiment on top of the ice. It's now way out in the lake back in 2008. It's a new lake. And so we're measuring discharge from that lake as well as what's going on up in the ice. But you can see the subglacial caverns are collapsing and causing it to open up very rapidly. So, and it's melting downwards as well. So over the 5 years, it's collapsed in one area, 56 meters of collapse downward. But the typical ablation rates or melt rates, if you get further up, are around 25 meters of downward melt over that period of time. So it's melting faster in the bottom, lower part of the glacier than the ice flow from the Wapta ice field can replace it, and hence the rapid horizontal retreat. But it's associated with that vertical thinning. And we're getting a new landscape emerging. We have a new glacial lake. It looks stable. I think it's going to survive. It's going to need a name someday. We call it Lake Monroe after Scott Monroe, a scientist who studied that area for many years. But as you can see, there's not much left of Peyto Glacier, and I think it will be gone by the end of this decade. There'll be ice still up in the top connected to the Wapta ice field, but not. The other thing, you can see that picture, that's from this September, is the ice is dark up top, and that's from the wildfires and soot deposition held in place by algae, which is blooming on the ice. It's kind of a dark algae. And this has increased the melt rates of the ice 10% higher than they would be just to the temperatures alone. But the temperatures have been very warm in summer. Snowpacks have been melting earlier, and hence these incredibly high melt rates. So that's a bit of what comes out of things like Global Water Futures Observatories. We manage the data and through a catalog we call GWF-Net, and because very diverse water data, data from indigenous communities, data on water quality, aquatic ecosystems, glaciers, meteorology, stream flow, lakes. The idea is that it's free of charge. It's open access data. We provide detailed information on the observatories, where it's regular data coming through from Met stations and others. We have them hooked up on telemetry, and we manage it using Whiskey software as deliberately chosen to be compatible with Alberta's system. And we're happy to provide a link from our data collection to that for snow surveys, stream flow measurements, anything you want. And then we also have access for facilities if people want to rent them or rent chemical analysis in the lab or things like that. There's opportunities to do that as well. This is what the GWFO webpage looks like as you zoom into it. We link the people, the scientific publications, the locations, and the data observations together in there with even the cost to rent equipment if that someone wants to do that. So just an example of that. Overall, we think that GWFO can be beneficial to Canadians in many ways. Basically, it's a facility, so the information from that can support improved flood, drought, and water quality predictions, floodplain mapping, design of irrigation, improved farming practices, responses to extreme events, restoration of our large and small lakes and wetlands across the country, uh, information foundation for water management strategies, and water for prosperity through industry and communities, and also a great way to attract and retain talented scientists in Canada. So I'll jump over to the modeling and prediction advances in global water futures. And there have been a variety of models. You can see it's alphabet soup there. I won't go into them too much, except one in particular I'm going to talk about is the mesh model, which is the one that we've set up over all of North America and many parts of Asia and Europe as well, and South America. But a lot of the work on mesh has occurred in Alberta to make sure it was fit for purpose in the river basins we have here. And in particular by adding glaciers and snowpacks and mountain slopes and wind flow acceleration over hills and other things, and handling the forest and organic terrain properly, including permafrost in northern parts of the province and up into the Mackenzie River. So it's we think it's one of the most sophisticated, widely applied models in the world for basin scale to continental scale water predictions. And so we've set it up on one basin that's of interest to all of us, the Saskatchewan River Basin, and at varying resolutions, 10-kilometer, but also on the small sub-basins. And done a lot of work on that because we've added irrigation and water management to it from the major reservoirs, as well as the natural hydrology. And we've forced it with historical climate as well as future climate information, so we can look at scenarios of what the basin's hydrology and water management might be under change. And we did the same for the Peace Athabasca and these others, but we'll just zoom in a bit on the current water balance for the Saskatchewan River Basin. You can faintly see the provincial boundaries on there, and but we lots of things that we knew, of course, is that the heavy precipitations in the Rockies, and it's not in the Palliser Triangle or the eastern Alberta prairies. And but the evapotranspiration demand is where the farming is, and so there's a mismatch between the provision of precipitation and the evaporative demand through crops in particular that makes farming so challenging in the Canadian prairies. The runoff generation is very much in the mountains and foothills, and making this classified as an exotic basin, much like the Nile, where we're really almost treating those rivers as canals crossing the vast river basins with very little contribution from local runoff until we get into eastern Saskatchewan and Manitoba. And then the prairie part of it dominated by rainfall, and mountain part of it dominated by snowfall. So there's nothing particularly new in that, though it's nice to see it mapped out in detail. But then we can dive into it and say, what are the sources of runoff generation in the basin, and where is that occurring? And so you can see the snowmelt runoff events very much restricted to the Rockies, rainfall runoff events a bit more into the foothills and out onto the higher elevation plains a little bit, and the rain on snow runoff events very much in the highest elevations. But when we look at the sources of runoff formation, either by frequency or by the percentage fractional amount of runoff over the basin, you can see that though snowmelt runoff is over half, but when we add the rain on snow to that and the mixed rain snow events, that we're looking at about 80% of runoff generation over the basin involves the snowpack in some way. And so given that our snow-covered winters are somewhat sensitive to a warming climate, that's cause for concern and hence focus. We're also able to separate out the glacier contributions to stream flow. And glaciers are absolutely beautiful and locally important to the hydrology. We're able to simulate the Peyto Glacier, for instance, its mass balance with some success. But when we look at the runoff contributions in various grid cells over the Saskatchewan Basin, you see it's small. We're looking at less than 1% even in those grid cells, top to bottom overall, and then that gets masked out by further contributions downstream. So the glaciers are important because they melt fastest in the hottest, driest weather, and so this is late summer and in drought periods, and particularly when you get to the North Saskatchewan River or Athabasca River, then they can have very important contributions to stream flow in late summer and early fall. Much less down in the Bow, Red Deer, and Oldman basins, and much less to come in the future. See, those mass balances are all negative through here. Blue is more negative than red in our color scheme. So we have this mesh model for the basin. We wanted to look at what the future hydrology would be, and not being climatologists, we thought that should be easy, but then we worked with some climatologists and worked up, found it's not very easy, but Environment Canada helped us with the CAN ESM global simulations, which are 300 kilometers resolution, and they spin those up over 1,000 years and then start running them historically from 1850s to 1950. They go to higher resolution around 1950, down to 50 kilometer resolution, and run that forward, and that's the CAN RCM4. So those are 50 kilometer resolutions getting more interesting to us as hydrologists. We can't do anything with coarser resolution runs, but it's still too coarse. They're going to miss some of the mountains. They're going to miss the convective storms and others. So we further bias corrected them in downscaled them using observational data and reanalysis data. So we had a 10 kilometer data set that reflected reality. And the CAN RCM runs themselves do not reflect reality. The precip can be off by 200 or 300%. The air temperature is off by 2 or 3 degrees Celsius. Once they're bias corrected, it's much better, but they still don't capture the extremes all that well. But that gave us 15 model runs to give us some idea of the uncertainty of what the future meteorology might be to force the mesh model for its runs. And with the caveats I had that I'm still not fully happy with the extremes. The temperature changes are the most reliable part of the model, and on the left-hand column you see it annually, and then for winter, spring, summer, and fall, the temperatures from the 80s to 2010 over the basin, and so no surprises for you there. And then the temperature changes by mid-century, which is really already starting, and then late century. And what's interesting is the temperature changes mid-century are strongest in the summertime and the wintertime, less so in the spring, in between in the fall. And overall, much more warming going on in Saskatchewan, Manitoba than in western parts of Alberta. Though when we zoom in a bit more, and particularly look at late century, we see that continuing more heating in the east than in the west, and the summer heating being quite substantial, with temperatures rising as much as 6 degrees, depending where you are in the basin. But again, reduced a bit in the springtime compared to the other times of the year. Fortunately for us, the precipitation is going up as well, or we'd be facing a disaster, and many parts of the world are, including parts of BC. But we get precip increases of 15-20% overall, though the devil's in the details of that. And so left-hand side is showing the precipitation as it is now, and then winter, spring, summer season, fall seasons there, and then the changes. And so overall they're up, but not everywhere all the time. And so we get a large increase in precip in the spring and in the fall, But summer, we're getting no increase or even a drop in precipitation by the time we get to late century for many parts of Alberta. Not so much for the mountains, but out in the plains. That's going to be problematic and lead to more severe droughts and low flows. I'll get into more of that in a bit here. We zoomed in with the model to the headwater river basins of the South Saskatchewan River, and you can see 500 subbasins for the Oldman, another 335 for the Bow, and another 237 for the Red Deer. And we forced the model with that bias-corrected CAN-RCM product to look at mid and 21st century changes in more detail. So let's look at the Red Deer River Basin. And this is just looking at the monthly values with error bars on them for the uncertainty range from the climate models. And what I'll call your attention to are the increases in precipitation in March, April, May, and June, but then the decreases in precipitation as we get into July, August in the future, moderated in mid-century, but much stronger by late century. And strong increases in temperature in summertime, July and August in particular, and in wintertime. When you look at soil moisture averaged over the whole basin, we see rises in the wintertime, and but then declines in April, May, large declines in June, July, August, particularly by late century. So that's evidence of drought. Higher evaporation rates in the spring, up through July, and then leveled off in August because their soils have run out of water to sustain plant growth, and late summer as well. Stream flow increases throughout the winter, but still small. Massive increases in March and April and May. And then June, initially an increase, then a decrease later on in the century, and substantial decreases in July, August, and a little bit in September. We'll see repeats of this to some degree over the Bow and the Oldman as well. But if we go into the Bow, looking at it at Banff and Calgary, and maybe we'll focus on Calgary because this is where you have a rapidly growing city and irrigation districts as well. And there we see the temperature increases greatest in the summertime and the midwinter time, moderated in the spring. But the precipitation increases are mostly in the spring and some degree early winter, and not at all in the summertime, but not really strong declines in precip in the summer there. Maybe a little bit in July by the end of the century, maybe August. We look at hydrological change at Calgary. Again, soil moisture remaining pretty high through the winter and spring period, but starting to decline June, July, August, September through the century as we move forward. Some of those declines even starting as early as May. In evapotranspiration, evaporative losses increasing earlier in spring, maintaining through the July, but then August moderated by lack of water. Same with September. These simulations are run without the irrigation operating in the model. So these are natural flows, natural runoff regimes. I should emphasize that. Stream flow increasing markedly in April and May. June is an initial increase and a decline, and a sharp declines in July and August. So a lot of what we saw in 2023 looks like that. We go further south to the Oldman Basin. Of course, it's a warmer climate down there. And if we look at it, the Oldman at the mouth, maybe to focus on what we see overall, substantial warming over the winter period, with winter temperature averaging close to zero now by the end of the century, instead of the -5 and -6 that's there currently. Then moderated warming in the spring, but very large increases in the summertime, with average temperatures jumping from the upper teens into the upper 20s in July and August. So it's going to be very, very hot. Precipitation increasing throughout the winter and through May and June, but then declining through July and August. And so that, again, that shift in seasonality, very important. The hydrological changes coming from that, I'll focus on the Oldman at the mouth. Soil moisture, again, these are natural conditions, so soil moisture levels starting to decline later in the century, right after February. So really getting rather dry with big drops in July and August and September. Evapotranspiration increasing from February up till June. A little bit of increases in July and August there because of some of those summer rains that will be occurring down there. And stream flow generation increasing quite a lot in the winter, markedly in March, April, and but May is when an initial increase by mid-century followed by a decrease in late century, and June, July, August with decreasing flows as the century proceeds, including September. So a little bit of a different story down in the Oldman, more challenges there, as you'd expect with the initially warmer climate, and a thinner area of runoff generation in the Rockies as well. The flow timing is the big one. The shift in stream flow timing, we look at whether we look at the Red Deer, the Bow, or the Oldman, is that by mid-century shifting forward by about 2 weeks, and by late century shifting forward by 4 to 5 weeks, maybe a little bit more in the Oldman at the mouth. And so that puts it out of phase with our current irrigation timing in many areas, and other needs for ecosystems and for communities, and will present challenges. So why the shift in timing? This is due to the loss of snow and ice in the mountains, reduced snow covered period, earlier melt, as well as a decline in glacier contribution. And so this means that the natural benefits of water storage that have been provided to us by snow and ice are declining over the century, along as entering a somewhat wetter but very much warmer climate. We look at water supply changes. There's a wide range of uncertainty from the various climate model forcings in there that we have to be apparent in. And by early to mid-century for the Red Deer, anywhere from a slight decline in average annual stream flow discharge to a more than 50% increase, averaging out about a 25% increase. For the Bow, increases under all scenarios, but smaller, anywhere from 5 to over 30%, averaging in about 12 to 13%. And for the Oldman, anywhere from a decline to a large increase of 55%, averaging in about 25% increase. So we have to be ready for a range of changes in here, and some of those scenarios don't have the precipitation increases that others would have, and so we have to be ready for that. So prepare for drought and hope for rain. The big shift will be the change from snowfall to rainfall, much more rainfall, including through the winter periods in here. Just showing the fractional changes in discharge that I mentioned there. When we take the 10-kilometer resolution model and look at it over the whole Saskatchewan River Basin, these are natural stream flows. And we can see the range from different scenarios of the runs, but in some cases higher peak flows, such as of the North Saskatchewan at Edmonton or the Bow near the mouth, but lower summer flows and much earlier flows and earlier spring flows in here. So it's that increase in winter and spring flows that we need to deal with, and some quite strong changes in the Red Deer River over that system. Then as you run downstream into Saskatchewan, the changes are still apparent down to Saskatoon. Of course, these are modified by reservoir operation, and we're just completing the runs with these deglaciation and climate scenarios that also include the reservoirs that are in place right now under the current set of rules that we've been able to deduce. And of course, the future rules on the reservoirs can manage this and deal with this in a wide variety of ways. So showing it with the current use is just a way to inform it. But for instance, Lake Diefenbaker in Saskatchewan in our simulations spills every month of the winter because of excess winter inflows. So but I'm sure that those reservoir operations in Alberta and Saskatchewan will change. And of course, there are new reservoirs on the books to be built and changes in operating rules that are already anticipated. So that's a rapidly changing area as well. So for now, we'll look at the natural ones and get an idea there. We look further north at the Athabasca River. Here it is at Jasper. And here we've got the runs with land use and climate change. And the land use includes glacier retreat, but also covers in our simulations a retreat of the forests due to wildfire and forest succession. And that's come maybe a little bit early for what we call the 2040 scenario. It's already happened in some big parts of Jasper now. But basically there, the LCC is the one to watch for. That's the land use and climate change, anywhere from an 8 to 16% increase in overall flows in Jasper. You notice the substantial drop in summer flows due to glacier retreat in the area and a shift in timing forward. When I look at it by 2085, the deglaciation has really kicked in, and at the town of Jasper, then we look at declining annual streamflow volumes of 14 to 6% because of deglaciation, even though it's become a wetter, rainier climate. And the summer flows, you look at the July-August flows, they're dropping from around 200 cubic meters per second to around 60 to 70 in that same period of time. So that's a dramatic change that will have important changes for the aquatic ecosystem. Further downstream, that gets mixed in with other non-glacial inputs, and so it's not as severe by the time you hit Lake Athabasca, as I'll show you next. Here are the same simulations for the Athabasca River below Fort Mac and the Peace River at Peace Point. And so if you look at the changes in water supply under the land use and climate change for the Athabasca, 11 to 36% increase at Fort Mac by mid-century, and by late century, 16 to 43% increase from what it is now. But the timing changes are massive in there, and the peaks are higher. So there'll be a change in the flooding regimes as well that we'll have to keep our eye on there. But also look at those late summer flows, some of them quite low through there, and lower than our, all of them are lower than our baseline from July 1st onward through there. So we have to be careful with that. I'll wrap up and hopefully leave some time for questions, but basically in summary, we found about 5 degrees or more warming is possible, or even likely by the end of the century. That will involve increased rainfall, decreased snowfall, but summers will be drier in terms of precipitation, which will be problematic. Glacier retreat and melt is accelerating, and the glacier contributions to water in the irrigated districts of Alberta is already small and are declining and will be negligible in a few decades. This is mainly going to be a factor in the most severe droughts, particularly in late summer flows. We're able to couple a detailed hydrological water resource model to bias-corrected downscale climate model to look at changing climate influences on water supply, and noting the rising temperatures and winter and spring rainfall, but declining summer rainfall. And the big impacts are changes in the timing of discharges, increasing roughly 15 days mid-century and 1 month by late century. The river discharges might decrease slightly or increase by up to half of current flows by mid-century. The annual discharges by late century might not change, or they might increase by up to 3/4 of current flows by late century. So we could have a lot more water, but it's not certain. However, what seemed to come out in all the scenarios was a drop in the June, July, August river flows, sometimes dropping by half of what they are right now because of the longer summer, the earlier snowmelt, the lack of glacier contributions. And for the Peace and Athabasca basins, things getting wetter up there in general, despite the impacts in Jasper, but stream flow, peak flows increasing 47 to 112% by the end of the century, and the timing and peak increasing by advancing by 2 to 6 weeks by the end of the century. but late summer flows dropping, and with the substantial declines in Jasper Park due to deglaciation. But overall, stream flows increasing 16 to 43% by the end of the century. So it's a very changed hydrology. This is not disastrous, but this is meaning we will have to manage our waters differently and thoughtfully, and have to account for the uncertainties in these futures, possible futures, but also the being able to adapt to both higher peak flows and lower low flows, and of course swings from droughts to floods that may become more intense. In fact, highly likely to become more intense. I put together a few ideas on some of the adaptations and solutions that we might look at. One is more water monitoring and prediction. We need more baseline data. We need more observations, provincial networks. The federal government can increase their networks that'd be great. Universities help where we can. And but also to develop comprehensive water forecasting and prediction models, including the human influences and water quality influences, some of the others. That's desperately needed. And I think we have a lot of the foundations to do that. We need to make sure our water management is informed by science, for whether it's new crop and water management developments. I didn't talk about that, but we have been showing how yields can be improved in dryland agriculture through improved snow management and residue management. That's one of the results at our GWF, getting this stuff implemented. And then new river water storage regimes to accommodate our flow timings and volumes that are coming. Remembering that groundwater is an unreliable resource for large-scale applications in Alberta. So we can't rely on the big aquifers that the Americans have in the past or others. That's got them into trouble anyway. We're going to have to adapt at scales from small communities to the province to river basins that are transboundary in nature. Changing timing of runoff, higher overall flows, lower summer flows, greater variability in flows, lower soil moisture in the summer, and wetter winters. And so we're going to need to make sure that our infrastructure is safer, more reliable, more resilient, and more efficient for our variety of purposes. And because we share our water with downstream provinces and with the United States, and further north with British Columbia, I think our transboundary agreements are going to have to become more robust. We're going to have to move towards more integrated river basin management on the SRB in particular, but the other basins as well, or we could risk failure to achieve our goals for sustainability of water and growth in our population, preservation of our environment, and adapting to these wild changes in climate in the prairies. So I'll wrap up there, and perhaps there's some time for questions.
Thanks, Dr. Pomeroy. And I think with that, we better move on. So thank you very much for that presentation and taking the time to address those questions so thoroughly. John has offered that if folks have further questions, that you can reach out to him directly. We will, if any other questions you have come up with now or in the next few minutes, please put them in the chat, and we'll pass them along to John as well. And with that, I'd just like to remind everyone our next seminar is going to be on Tuesday, October 22nd, and that will be with Dr. Yanni Akalilu and Naomi Tam from Environment and Protected Areas, and they'll be presenting on Atmospheric Deposition Monitoring Network, the past, current, and the future, a review of selected ion concentrations from precipitation between 2011 and 2020. Finally, if you're not on the mailing list for these presentations, please send an email to the Office of the Chief Scientist mailing address, epa.ocs@gov.ab.ca. And again, thank you, Dr. Pomeroy, for a very thoughtful and interesting presentation. Thank you, everyone, for joining.